We just solved our very first heat equation in the last lecture. And at the very end, I said, what if our boundary conditions changed just by a little bit? That's what we're going to do today. And the result is actually going to surprise you, I'm pretty sure. So we have this material, the solid substrate, where we want to measure the heat transfer through. And last time, we did a problem where the ends of the material were dunked into ice bath water, 0 temperature. So both temperatures were fixed at 0 for time t bigger than 0. This time, I want to solve a very slight variation of that problem, where instead of 0 temperatures on both boundaries, one of the boundaries is going to be subjected to a non-zero temperature, a hot bath reservoir, just like that. So like I said, in the last lecture, it was 0 and 0 on both ends. In this case, all we are doing is taking one of the boundaries and subjecting it to a hotter, warmer temperature. And you would think that's an important problem for science and engineering. We're always not dunking our material into ice bath water. Sometimes we're going to have a warmer temperature boundary that is subjected to a warmer reservoir. And therefore, you'd think that this is a problem that we should be able to solve very easily. So let's try to solve this equation the same way we did last time, where we're trying to solve for the temperature profile inside the slab as a function of position x and time. Just like that. So for every problem that we're going to do for the rest of this class, it's very important to have a physical understanding of what it is that you are solving for. So first, forget about all the math and just try to physically understand what is happening in this problem. So first, we have some initial temperature profile. To make things easy, let's suppose that initially the temperature profile inside the slab is all the way equal to 0. So it's cold ice bath, 0 temperature all the way through. So it's specified here for all positions x from 0 to L at 0 time, initially, the material is 0 temperature all the way across. And at time t equal to 0 plus, instantaneously, the left-hand reservoir is contacted with a warm temperature T1, and the right-hand boundary is contacting still ice-cold bath water at 0 temperature. Now, if I were to ask you to plot the temperature profile between 0 and L as a function of x, what would it look like? So initially, I just gave you that the temperature is 0 all the way across. We can plot that in there. So initially, temperature is all the way 0. So it's just this horizontal line that runs all the way across. So that one is your initial temperature at time t equals 0. Now, at time t equals 0.000001 seconds, so the moment after 0, the left-hand boundary must jump to the temperature T1 because that's a boundary condition. All of a sudden, the material on the left-hand slab is contacting T1. It must be at that temperature for the rest of time. Therefore, we know that the temperature must jump to the value of T1 at the left-hand boundary. And we also know that the right-hand boundary must also be fixed at 0 temperature because those are the two boundary conditions. Now the question is, how do you connect the 2 points? Now let's think about this again physically. Forget about the math for a moment. If you were a little tiny molecule sitting right here, at that point, observing the temperature of your neighbors and yourself, at time t equals 0.000001 second, do you even know that the temperature changed the boundary long all the way over there at x equal to 0? Probably not. Probably not. Because you still think it's 0 temperature because your neighbors are also 0 temperature all the way out here in the bulk of your material. And the warm reservoir, that's way out there. That heat has not taken the time to transport to where I am located here, and therefore the temperature is still going to be 0 at that point. And the same can be said here, 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 all the way until you get very close to the boundary where the temperature has to go, whoa, way up to T1. Okay? Just based on that physical intuition, again, no math at all, just physical intuition, we know that the temperature profile must look something like this, just like that. So 0 all the way until very close to the boundary, it has to go way up to T1 because that boundary condition must be obeyed. So at time t equal to 0.0001 second, that's what the temperature profile would look like qualitatively. Now, let's wait a little bit more time, a moderate time, a couple of seconds. Now what do you expect? Now, this molecule all the way sitting over here on the middle of the slab might start to feel a little bit of heat, right? Because you've waited a little bit more time, the heat has penetrated into the material a little bit longer. So again, it has to connect these 2 points, but the slope and how it connects those 2 points will start to look a little bit different. I'm just using arbitrary time, but the point is you have 0 time, 0 plus, and then a moderate amount of time. The temperature profile will look something like this. Again, just based on physical intuition. Now, final question. When you wait an infinitely long time, when time t goes to infinite amount of seconds, then how do you expect these 2 points to be connected to each other? The easiest way to connect 2 points is by a line. Okay? Now, in general, it doesn't have to be a line. It happens to be the easiest possible way to connect 2 points, and you're going to later see that for this particular problem of 1D heat conduction, it must be a line for a homogeneous, isotropic, uniform material that we have. But in general, it doesn't need to be, and you'll see exactly where this linearity comes about. So in general, you don't need to know whether it's linear, but all you need to know is there's going to be some kind of steady state temperature profile at the very end when you wait a very, very, very long time. So that would be called your steady state temperature profile. Again, steady state means nothing is changing with time anymore. Things are still changing with space. The temperature is going down as you go from left to right, but nothing is changing with time. That's steady state. Equilibrium will be nothing is changing with time and space. For this particular problem, it would actually never reach equilibrium because the construction of the problem is one in which the baths are infinite in size. The left-hand boundary is always T1, the right-hand boundary is always at 0. Now, in reality, heat baths and heat sinks are not infinite in size. And so each of these baths and reservoirs that it's connected to would also have some finite volume. And eventually, the temperature over here on the left will start to go down because it's going to release more and more heat into the material and eventually go into the ice-cold water, which will start to increase in temperature. And eventually, both reservoirs will reach some intermediate middle temperature between 0 and T1 based on the volumes of the 2 tanks. And then you'll have one uniform non-zero temperature that goes all the way across. So just be a flat temperature profile, and then you're at equilibrium. Nothing is changing with time and position. But for this toy problem, we are assuming that the reservoirs are infinite in size, and therefore it will forever maintain this temperature T1 on the left, and forever maintain this temperature 0 on the right-hand side. So we'll reach this steady state profile that varies with space, not with time. I'm going to call it T steady state as a function of position x. Now, I hope you understand the physics of this picture. This is the progression of time. Initially, it's at 0. At some small time, it starts to lift up. The boundary condition is now satisfied, and at very, very long times, it achieves a steady state profile. Now, this is the most important part of the problem. Before you do any math, there's no math here, just pictures and just physics. Do this first, always. In fact, for any research problem that I have always worked on, I always draw a picture because the physical intuition and the physical acumen that you have about a problem is so important. If you get this picture wrong, the math may still work out, but you will have no idea whether it's wrong or right. And the physics and your intuition about what it should do will guide every step of the math along the way. And at the very end, when you check your answer to make sure it's physically consistent, if you don't have the physics in mind, you're not going to be able to make much mathematical progress to see whether you have the right answer or not. So this physical picture is incredibly important for you to be able to draw. And do this for every single problem. Now that we've done this for this particular problem, now it's time to start digging into the math. So all we've done is change the boundary condition on the left-hand side compared to our lecture from last time. So all we're going to do, write down our governing equation and our boundary conditions and initial condition. Here is the governing equation, the 1D heat conduction equation, or simply 1D heat equation. Initial condition, for all x at initial time t equals 0, the temperature is 0 everywhere. I gave you that. This doesn't have to be 0. I just made it 0 for simplicity. It could be some arbitrary function f of x like we did in the last lecture. For simplicity, I'm just going to keep this 0. Second condition, which is the first boundary condition on the left-hand side, is the sole conceptual difference in this problem. Before, this right-hand side was equal to 0. Now it's equal to T1. On the other boundary, at x equal to L, it's still the same. It's dumped into ice-cold water on the right-hand side. So really, the only fundamental difference of this problem is that boundary condition on the left-hand edge. So a very small deviation from what we did last time. Literally same equations, same conditions, except for a small little thing. We've just made the temperature on the left-hand edge equal to a non-zero number. That's it. That's the only seemingly small little minor change we did to the boundary condition. So surely, separation of variables should just cut through this problem and we'll make a lot of progress like we did in the last lecture. Because, come on, after all we've done is just change this boundary condition to a non-zero constant number. What harm could it do? So let's repeat what we did in the last lecture. Now remember, we did in the last lecture, we did separation of variables by assuming that the temperature profile could be written as a function of x and a function of time, multiply them together as a product, and we've separated the time part and the space part of the ODE. Let's write that down and then write down our full solution like we got last time. All right, just carrying through as before, surely, because separation of variables must work for this equation. We're going to write down our temperature profile as a product of these two functions, as a function of x and as a function of time. Like I said, we're going to plug this into this equation. You put all the space variation on one side, the time variation on one side. The only way you can make those two the same is if they're equal to a constant. We call that constant negative lambda squared. Boom, all of a sudden, we have two separate ODEs to solve. The first ODE is a time ODE. It looked just like this. And the solution was a decaying exponential. Just like that. And then our other ODE was a space ODE as a function of x. Just like this. And that gave sines and cosines. Just like that. Okay, so far, nothing has changed. Honestly, you don't even have to copy this down because from the previous lecture, it's the same. Why? Because we have the same governing equation. The part that we change, which is the boundary condition, comes after this step. So everything up from here is the same. So why would you expect it to be any different? It's not. It's the same. Completely the same. We take these two equations together, multiply them, get our temperature profile. Just like that. Our total temperature profile is a product of e to the negative lambda squared alpha t times sines and cosines. And I've just used a new constant of integration, a1 and a2, again, combining a, b, and c together and grouping them so that I can have two constants of integration, a1 and a2, each multiplied by a cosine and sine. So everything up until this point is simply working on the governing equation. We haven't even touched the initial conditions or the boundary conditions at all. And here's the step where we apply those conditions. We have a1, a2, and lambda, which are unknowns. Three unknowns, three conditions, 1, 2, and 3. So, in theory, we should be able to make progress. And last time, if you recall, we applied this boundary condition at x equal to 0 as our first boundary condition because that allowed us to remove the sine, that died, cosine became 1, and therefore it allowed us to say something about one of the constants of integration. So let's try boundary condition on the left at x equal to 0 and see what it does this time around. So this is our boundary condition. At x equal to 0, for all time t, the left edge of the slab is contacting a heat reservoir that's maintained at a fixed temperature T1. So all we do is plug in x equal to 0 into this expression that we have right here. The sine of x dies, cosine of 0 becomes 1, and therefore all we have left over is this term, right? Take a moment to check the math. Again, at x equal to 0, cosine becomes 1, sine becomes 0, it goes away. So the a2 sine term completely goes away. All we're left with is a1, and this exponential term must be equal to this constant heat reservoir temperature T1. So at this stage, you conclude and say, okay, well, we know the value of a1. Just like last lecture, we found the value of a1 using the boundary condition over on the left-hand side. Just like this. So if our constant of integration is equal to T1 e to the alpha lambda squared times time. Are you guys happy with this? Think about this for a moment. A1 and A2 are constants of integration. Constant. Constant. It has to be a constant. A1 and A2 cannot be a function of x or t. So here, apparently, I'm getting a constant of integration that is a function of time? Whoa, 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 whoa. Something bad is happening. What did I do? I did the same thing as before. I mean, separation of variables worked so well last time. It just cut through the problem, and I did nothing wrong. Just separation of variables. I mean, everything here is the same as last time. And then all of a sudden, I apply this boundary condition, and I'm now getting a constant of integration a1, which is a function of one of the independent variables, time. You can't have that. You cannot have a constant of integration that varies with time. That's just a contradiction. You can't have that. It's a constant of integration. So something's not right. And in fact, this is all wrong. I'm sorry, I'm going to draw a double cross here because it is so disappointing. Wow. We spent a week learning Fourier series. We spent another week deriving the heat equation. We just covered an entire lecture on separation of variables, learned about superposition, eigenvalues. Oh my gosh, my head was about to explode. And then finally we got this answer, which had a bunch of mathematical gibberish. And then you're telling me that it just fails for the smallest possible thing? I mean, look, all we did was change that little thing, And all of a sudden, separation of variable just completely collapses and just falls on its knees. You've got to be kidding me. Give me back all those 4 weeks that I learned Fourier series, separation of variables, heat equation. It's crazy that a small little change to the boundary condition and nothing else will just completely destroy separation of variables. And you can check, you can try the other 2 boundary conditions. It's not going to help you. Try plugging in the other boundary condition, and it's not going to help you. The initial condition isn't going to rescue you either. So fundamentally, it has failed. Separation of variables has failed in this case. Why does it fail? Think about it for a little bit. So this is pretty depressing that the thing we spent so much time on has failed for the smallest deviation to a successful case. So why did separation of variables fail? And what could we do to fix it, if we can even fix it? Let's return to the original physical picture that we drew earlier. If we wait a very, very long time, the temperature profile should approach this steady state profile TSS as a function of x only. So here's a new idea to see if we can work around this issue of the boundary condition. A new idea. That new idea is, suppose that I take the full solution, the temperature profile as a function of position x and time, and break it down into a sum of 2 functions. The first function is called the transient part, and the second part is the steady state solution, the same solution that we drew earlier for the infinite time result. So essentially what we're creating is a deviation variable called t transient, where it's the full solution and subtracted off of that a steady state part, such that the total solution temperature profile is the deviation part, the transient, plus the long time steady state solution. Now you might ask, why would you do something like that? Because I can. We solve differential equations by guessing. We're going to guess the form of the solution, and we can do this because the equation's linear. It's a linear differential equation. Again, go back to the classification all the way back to lecture 1. For a linear differential equation, we can superimpose solutions and add them together. That's perfectly okay to do. So what we're going to guess is that we're going to be able to remove the steady state part of the full solution out of the way and take everything else and jam it into this transient temperature profile, T transient. So what we can do is to plug this equation back into our original PDE and see what happens. Just substituted the assumed form of the new solution, our new idea, into the left-hand side and the right-hand side of the governing equation. Now, I've explicitly written the temperature TSS as a function of x, the steady state solution, explicitly only as a function of x, right? Because that is the steady state solution. It doesn't depend on time. And therefore, when you take the time derivative here, this term will go away because you're taking a time derivative of a function that's only of x. And therefore, that term goes away. So on the left-hand side, we're just going to have a partial derivative of t transient with respect to time. And the right-hand side, we're going to have 2 terms. Now, both terms will stay here because this is an x derivative. Just simplifying now. Left-hand side has the t transient, time derivative. Right-hand side, we have the space derivative, second derivative with respect to x, or the transient part, and the steady state solution. Now remember, this t transient is a function of position and time. And therefore, these are both partial derivatives with respect to time t, with respect to position x. This last term on the right, t steady state, is only a function of position x. Again, this is the long time solution where there's no more time dependence. The time decay has all been done, and therefore it only depends on position x. So this derivative is a normal derivative, a standard derivative with respect to the single variable x. That's why this is not a curly script d, it's the normal letter d for the derivative. So when you look at this, these two terms on the left and the first term on the right, this kind of looks like the problem we've already been solving. And actually the same problem we solved last time, in the last lecture. And this term over here on the right, this is kind of the new term that we've inserted because we've removed the long time steady state solution from the original problem. So here's another idea. What if this part were equal to 0 and this part recovers our original heat equation? If that is true, we may be able to somehow get rid of this boundary condition that caused problems. So let's see what happens. So we're going to basically solve now two separate problems. One problem over here that I've underlined with pink. This problem we need to solve. That's the normal heat equation-like form. On the right is just a second order ODE equal to 0. So it's a homogeneous linear second order ODE. We can solve those two problems. Let's do that. We get these two solutions. First, this term on the left, the t transient solution. That is identical to what we did last lecture, identical to what we did for the first part until this failed. Remember all that stuff that we wrote up here on the upper right? Separation of variables, you have the space OD, the time OD, you put them together, boom, you got this expression. That's just a solution to this part of the equation before applying boundary conditions, initial conditions. It was after this step where everything failed. Let's keep it here for now. And actually, some of you might be wondering, I feel like we're going in circles. We're doing the same thing, we moved the steady state part, but then you did the same thing and then out came the same equation. Are we going in circles? Not quite, because we have this extra thing over on the right-hand side. So this other solution, where the second derivative of your steady state is equal to 0, is just going to be direct integration, which is equal to mx plus b. Okay, direct integration. So you have a second derivative equal to 0, you integrate twice, you get two constants of integration, e and f, and that the e term has a linear factor of x out in front, and then f is just a pure constant, right? mx plus b, just the equation of a line. So now everything connects back to our original picture that we drew. Now, I asked you, I have 2 points, one at the boundary at t1, one at 0. The easiest way to connect those 2 points is by a line. Here's the line. mx plus b is an equation of a line. So we have a line that connects these 2 points. Now, remember when I said, in general, it doesn't have to be a line. It could be any function. You don't know if it's linear. And this is where it shows up. This is a situation where your steady state solution was equal to, the second derivative of your steady state solution was equal to 0. Now, there are many situations. For example, if you have a reaction term. Suppose there was a chemical reaction, a 0th order chemical reaction. Just like that, where K might be a chemical reaction that adds heat. So like an electrical wire inside your slab that emits a constant flux of heat into the material. So you have this wire, it's conducting electricity, it heats up, and therefore your slab all of a sudden has internal heat generation at a constant rate given by K. So K is a constant. If you go through the exact same procedure, over here, you're going to get that the second derivative of t steady state, dx squared, is going to equal K. And now, you're going to get this guy, k to pop out. And so now, if you integrate this equation twice with respect to x, you're going to get a parabola. You're going to get a quadratic equation. K times x squared, blah, blah, blah. So now, that's a situation where these 2 points aren't connected by a line. And that also kind of makes sense, because now I have these 2 boundary conditions plus some constant sink or source of energy into your system. It's being supplied. So therefore, your temperature, you wouldn't expect it to be linear, because now at every point along your material, you have this constant source of heat, of temperature being injected into every point along your material. So you wouldn't expect it to. For this particular case, it will be a quadratic steady state solution. Okay? So that's what I wanted to say. It doesn't always have to be linear, but you need to know that you will have some kind of steady state solution that comes out of it. All right, so let me just erase the k's because that's going to be confusing, and we'll return to the rest of the solution. In this case, we don't have a chemical reaction, we don't have any sources of temperature or energy, and therefore we have the linear mx plus b equal to the rest of the stuff. So now, all we need to do is this equation is our transient solution, and this solution is our steady state solution. Now, our total temperature profile must satisfy these initial condition and boundary conditions. Let's go back to the troublesome boundary condition and see what it gives us, because last time this is a step where everything got screwed up. Let's apply boundary condition number 2 with this new solution and see what happens. Here we go. Boundary condition on the left-hand side at x equal to 0 for all time t is equal to t1. This is where the nightmare began earlier. It didn't work out. Let's see what happens this time. So we're going to plug in x equal to 0 in this equation up here. X equal to 0 means over here in the transient, the cosine will stay because cosine of 0 is 1, sine of 0 is 0. So the b, e to the negative, la la la, that will stay. Second term, t of x equals 0 is the steady state solution. Boom, the steady state solution is ex plus f. We're going to plug in x equal to 0. All we're going to get is the constant f to come out. Let's write that down. Just like that. So things are different this time, which is really exciting. Previously, we didn't have this factor of f. It was just b times e to the negative of the argument is equal to t1. That's what we had earlier. And that's where everything got screwed up, because we needed to put exponential on the other side, and that's what caused all the problems. But now we have this factor of f coming from our steady state solution that could actually rescue us. So first, let's go through our train of logic. On the right-hand side, we have a constant, T1. It is a constant temperature, and it cannot vary as some function of T or X. Over here on the left, this B times E exponential term, the argument has a time in it. Therefore, this term has to die. We can't have any functionality of time present on the left-hand side because the right-hand side is a pure constant. And this equality needs to hold for all time t. That means that the only way that we can make this true is if b is equal to 0. Because otherwise, we will be left with a time functionality, which can't happen. Again, that's where everything went wrong last time. And we can have b equal to 0 in this case. We could afford to do that because we have f to our rescue. So if f is equal to t1, this boundary condition is totally satisfied for all time t. Good. So now we found one constant of integration, b must be 0. We also found f must be equal to t1. So let's write that in there in the solution above. So first, this term, completely gone. because b is equal to 0. Secondly, f is equal to t1. Let's make that replacement, just like that. So we're making progress. Now, let's consider the other boundary condition and see what that gives us. Let's do boundary condition on the right. Here's our boundary condition on the right-hand side, x is equal to L. So all we need to do is to plug in x equal to L here. So we get sine of lambda L, the steady state solution, E times L, the boundary size. Let's plug that in here. Just like that. Transient solution, steady state solution, the sum of those two things evaluated at x equal to L must be equal to 0 on the right-hand side. Same train of logic. Everything here is a constant. E is a constant, L is a constant, T1 is a constant. We have here an exponential term. That needs to go away. Now, there's two ways to make this term in yellow go away. One way is to make c equal to 0. If you make c equal to 0, this term, the transient term, goes away and you get the trivial solution, the worthless solution. So we don't want that. But you know that the alternative way to make this term go away is the signs crosses 0 every n pi cycles. Again, this is where the eigenvalues and everything came in from last lecture. The same thing here. The alternative is if the argument of the sign was equal to n times pi, where n takes integer values, and therefore we get our eigenvalues lambda L is equal to n pi over L. Same thing as last time. If these values are satisfied, then this entire first term on the left completely goes away, right? So now all we're left with is the term in the middle. EL plus 1 is equal to, EL plus T1 is equal to 0. That's very easy to satisfy. Just like that. The constant E in our steady state solution apparently is just the temperature T1 that we specified divided by the domain size L. So this boundary condition on the right at x equal to L gave us two pieces of information. First, it told us the lambdas, which is great, and it also told us the rest of the steady state solution that we needed previously. So at this stage, we're making a lot of progress because now we know what the E is right there, and we know what the lambdas are. These lambdas tell you there and there. Okay? So all that we're left with is this constant C. So let's clean this up because this is making me a little bit nauseous with arrows and everything going on. I'm going to clean this up and we'll find the values of C to complete the problem. Okay, we're almost done with our problem. We're so close. We have this solution. We've applied two boundary conditions. We obtained our lambdas, which I substituted into here. We obtained our steady state solution. We found our E and F. We found our B constant. All we have left is one unknown constant, C sub n. We have, luckily, one initial condition left over to obtain those constants. Let's apply the initial condition to complete the problem. Here's our initial condition. For all position x at initial time t equals 0, everywhere inside the domain is equal to 0 because the entire slab is at ice cold water, 0 temperature all the way across. We're going to evaluate time t equals 0. This exponential just becomes 1, and therefore all you're left with is the C sub n, the coefficients we're trying to find, times the sign, the entire steady state solution. This whole thing must be equal to the right-hand side equal to 0. But all you realize here is this is just a Fourier series. That's it. Now you can clearly see the Fourier series. I have a bunch of signs and coefficients out in front is equal to some function of x on the right-hand side. That's all we've done. And interestingly, everything here is just the minus of the steady state solution, the long time solution as you wait going out to t going to infinity. So ultimately, we're going to find our constant c sub n using orthogonality, which will look like the following. Just like that. So we've taken orthogonality, done a Fourier series, obtained our c sub n, which is equal to this integral. You're already experts at this because you all know all about the Fourier series. So we are done. We have the temperature profile, which is equal to this long, ugly thing, and your coefficient c sub n is given by this integral for each index n. So ultimately, this, you would plug into your c sub n and do those summations, just like you would do for any Fourier series, and there's your solution. Now, there's actually a lot of things I want to talk about with related to what we just found. Where should I begin? First of all, what we've done is something kind of remarkable. Remember when it failed earlier? It failed because the boundary condition was not equal to 0. And essentially, we broke up our problem into two separate parts. Let me draw a picture. We had our problem that we wanted to solve, which was this original problem, boundary T1 on the left, 0 temperature on the right-hand side. We tried solving this with the heat equation, and we failed because this boundary condition on the left somehow screwed us over. So we split this problem up into two parts. In the first problem, we had the transient problem. And there, we had boundary conditions that were 0 on both ends. Now, we added that together with a steady state solution, which is at t going all the way to infinity, where this boundary condition got absorbed into the problem over here. And the right boundary condition just comes straight down. So the key point is that we solve the heat equation over here with 0 boundary conditions on both ends, right? In particular, with the boundary condition on the left equal to 0. If you go back to your notes, that's essentially what we did. We set that whole term on the left, right? B times exponential negative alpha lambda squared t. That whole term was set to 0 because that's essentially what we've done here. We've solved the heat equation with 0 boundary conditions on both sides. This over here on the right, that was just direct integration, which is easy to solve and easy to incorporate this T1 non-zero boundary condition. So the important point about separation of variables and the heat equation is that you can solve it when you have 0 boundary conditions. More properly, what are called homogeneous boundary conditions. This is a very, very important point. So the heat equation can be solved using separation of variables in the Fourier series if you have homogeneous boundary conditions. In other words, 0 on both surfaces. The non-homogeneous part, which was this T1, was completely taken care of by the steady state temperature. So remember back to second order ODEs, and remember how we had the full problem with a non-homogeneous term g of x. We separated that into two other problems as well, the homogeneous differential equation and then the particular solution. We had the homogeneous solution, the particular solution, right? Close analogy here. We're solving the homogeneous solution on homogeneous boundary conditions using separation of variables. And we're finding a particular solution, sort of. Again, loose analogy, but it's there. We're taking care of the non-homogeneous term or non-homogeneous boundary condition by solving a separate problem for the steady state profile. So this is incredibly important. So separation of variables don't get me wrong, is an incredibly powerful technique. And I made that whole drama with, oh, it failed, and I crossed out X's everywhere. No, it's perfectly fine. It's just you, as the user, needs to be aware of this condition. You can only use it when you have homogeneous boundary conditions. If you don't have homogeneous boundary conditions, you can't do this approach. But don't worry, just like we did here, you can take deviation variables, take out the steady state part. You can massage the boundary conditions in just the right way such that you can always have a homogeneous problem that you can solve. So this is a very important point. And a seemingly small difference to the boundary condition can make a dramatic impact on how you solve the problem. I mean, this is a totally different, it seems like a different way of solving the problem, because at step 1, you needed to remove a steady state profile. So just from a seemingly benign change to a boundary condition results in a completely different way in which you solve the problem. Now, I wanted to plot, and actually not wanted to, I will plot the solution. But one more thing I wanted to mention is that look at the Fourier series coefficients. What we did over here was we obtained the Fourier coefficient C sub n, and it was a Fourier series for the steady state profile. It's the negative of TSS. Recall the other problem we did, where the initial condition was some function f of x. And we developed the Fourier series right here, so f of x went right here. In this particular case, we are developing a Fourier series about the steady state profile. So what this means is that we are perturbing the solution about the steady state solution. And you can see that. Look at the solution. Now we're going to start to tear apart the mouth. Look at the solution. We have the C sub n's, which has in it a model of the steady state solution. It's minus t steady state. So at very, very small times, again, at 0.0000001 seconds, this term is going to largely cancel the steady state solution over here, because this is TSS. This C sub n sine n pi x over L, according to this, will be largely modeling negative of t steady state. And for small times, the exponential is going to be close to 1. Therefore, for very, very small times, this term will cancel this term largely, except for at the boundary. That's why it's 0 all the way across. Because these two terms are canceling each other for most of the domain, except very close to the boundary, where it just shoots up to t1. And as you wait more and more time, this exponential function will start to dampen this negative of t steady state, and then this steady state solution, which is all independent by itself, standing over this island, will start to get more and more and more important. So early on, this transient solution is doing a lot of work because it's canceling, it's removing the steady state solution and then adding to it its own to satisfy boundary conditions. And as you wait in time, that dampens less and less and less, and the steady state solution gets more and more and more important, this top solution, TSS, and then when you wait a very, very, very long time, this whole first term completely goes away, and all we're left with is this steady state solution. Okay, enough talking. Let's plot this solution. I want to show you, it's a pretty cool temperature profile. Let's move to the screen, and I'll show you what this looks like on code. What we've done is to first define a couple of parameters. First, the length of the slab set equal to 1, so L is equal to 1. The thermal diffusivity set to 10 to the minus 2. The number of terms in this Fourier series set to 100, so we're going to take 100 terms in the Fourier series. We've set our spatial resolution, the number of animation frames, because I want to solve this as a function of time and animate it. And otherwise, I've set the left-hand boundary, T1, the warm reservoir, to be a temperature of 100. And therefore, that sets our long-time steady state solution as negative 100 divided by L, which is 1. So negative 100x plus 100. And you can see down here that when I defined the Fourier series coefficients, I have here just the negative of the t steady state solution times sine, and lambda is just simply defined as n pi over L, but L is equal to 1, so it's just n pi. And I'm calculating my coefficients b sub n right here, and just sticking it right into this temperature profile. And so now we can evaluate this code, and here it is. You can see that at early times, the temperature is very close to 0 all the way across the domain, and then very close to the boundary at x equal to 0, it jumps up to 100. And I'm plotting this as a function of x dimension along the x-axis from 0 all the way to L equal to 1. Now, the black line right here is the final steady state solution. That's the mx plus b solution, where the boundaries are pinned at 100 degrees on the left and 0 degrees all the way on the right. So those 2 points are always satisfied across all time. Now, let me just play this video again, and I'll scroll down a little bit so you can see exactly how I implemented the time part. You can see that I'm adding each of these coefficients with sine lambda x times the exponential part, so exactly translating what we have on the board over to code. And we're just doing a loop in time from 1 to number of times, nt, and just updating that plot on every time loop. Let me just play that again. So early on, you actually saw all those wiggles. I hope you caught that. At very early times, you see all these wiggles like you saw in the previous example, because you could see the Fourier series and the coefficients oscillating at early time, trying to map this 0 and all the way jumping up to 100, that initial condition, just as the left-hand boundary changed to 100. And as time goes on, you can see that the temperature profile slowly evolves and gets closer and closer to the steady state temperature. And it's literally like we described earlier. Early on, the transient solution is removing the steady state solution. And as time goes on, the exponential starts to kill off that transient term, and you approach closer and closer to the final steady state solution. So it's a solution that kind of deviates away from the steady state solution, and you see the exponential that decays and gets slowly closer and closer to the final steady state solution. Once again, I just think it's just so cool when you see all this mathematical gibberish actually start to make sense when you animate it, when you plot it, when you graphically illustrate to something that you can actually see physically that checks out with your physical intuition. This is something I always recommend for all of science and engineering. Regardless of what career you go to in the future, you should always have your physical intuition guide the mathematical language that you write down. This overall process that we just went through, where we homogenized this boundary condition to remove it in the transient part of the problem, to push this boundary condition into the long-time steady-state solution, is a part of a theorem or theory called Sturm-Liouville theory. And it is an approach that we took in this lecture of taking a non-homogeneous boundary condition and homogenizing it. This aspect of the boundary condition is an important part of the Sturm-Liouville theory. Now, one more comment. We broke up our overall solution into two terms, a transient term and a long-time steady-state solution. And this superposition and a linear combination of these two solutions can only be done for linear differential equations. If you were to have a nonlinear term like t squared or t times partial derivative of temperature with respect to x, that kind of nonlinearity will automatically preclude you from doing an approach like this. Because when you think about it, if there were a term that looked like t squared, temperature squared, then if you were to take the quadratic of this equation by squaring it, you'd get this squared plus this squared, which is fine, but you also get a cross term. You get t transient times t steady state. You get a product of those two things, which means that you're getting cross terms that you can't account for when you have nonlinearities in your equation. So that's why very early on in the class I said linearity or nonlinearity of the differential equation is one of the biggest differentiations in terms of what approach you can take. Because our equations are linear, we can take this kind of approach of superposition. Okay, well, here is the lecture on Sturm-Liouville theory. And when you have this very small, minor, seemingly minor change to your boundary condition that dramatically changes the course of the solution that you have and the overall approach. So separation of variables still works. You just have to be a little bit insightful and creative early on in the problem to make it so that separation of variables will still work out with zero boundary conditions on both sides. All right, I hope you have a nice rest of the day, and I will see you next time.